To video lecture. Myself Ashwini RK, Assistant Professor, Civil Department, Rogni College of Engineering and Technology. Today we are going to see about the track stresses. So a railway track is a composite structure which consists of rails, sleepers, sleeper fastenings and ballast, and finally western subgrade. Each element of the railway track is subjected to a repeatedly applied deflecting and bending loads as wheels of train passes. Track modulus. Track modulus is an index of stiffness of track and it is defined as a load per unit length of the rail required to produce an unit depression in the track. It depends upon the gauge, type of rails, density of sleepers, ballast and subgrade. Initial load of about 4 tons results in greater initial deflection which causes a gap between rail and sleeper and between sleeper and ballast and voids in ballast depending upon the track maintenance. This modulus is initial range is called ITM. The load beyond 4 tons is in elastic range and it is called as EM. Track stresses. Stresses are produced due to wheel loads, dynamic effects of wheel loads, hammer blow due to overbalance of driving vehicles of locomotive, horizontal thrust due to nosing action of the locomotives, pressure exerted by the flanges of wheels on sides of the rails due to irregularities in the track, additional stresses on the curves. Dynamic effect of wheel loads. The speed or the impact factor is a measure of effect due to speed, vibration of rails under moving loads of vehicles. The impact factor is given by impact factor is equal to V divided by 18.2 root mu. Is used IR up to 1966. V is the speed in kilometer per hour. M is the modulus of track in kg per centimeter square. For speed up to 100 km per hour, impact factor is equal to V square divided by 30,000. And for speeds greater than 100 km per hour, impact factor is equal to 4.5 V square divided by 10 power 5 minus 1.5 V cube divided by 10 power 7. V is the speed in kilometer per hour. The wheel load is a multiple by this impact factor for accounting the dynamic effect due to the speed. Stresses in rails. The stresses in rails do not greatly alter by the number of sleepers under the rails, and the sleeper spacing has smaller influence on the stresses in the rails. If the section of the rail is constant and the sleeper spacing is uniform, the stress in the rails under the wheel will be constant. If the vertical loads are eccentric, the BM will be accompanied by torsion of beam. Hence, torsional stresses in the head and foot of the rails are developed due to eccentric vertical loads. The lateral thrust at the rail head produces lateral deflection and twisting of the rails. The lateral movement of rails is opposed by the factors like friction between rails and sleepers, fastening, ballast sides and ends of the sleepers. A small wheel with a light load can be produced as much as plasticity in the head as large wheel with heavier load. The maximum shear stress below contact surface on BG under diesel locomotive is 36.25 kg per millimeter square. The minimum ultimate tensile strength of rail is equal to 72.42 kg per mm square. The assumed yield point is 42.52 kg per mm square. In vertical bending, the permissible stress is 23.62 kg per millimeter square. Stresses in sleepers. Stresses in sleepers depends upon wheel load. Greater wheel load, higher will be the stresses. Weight transfer from wheel to wheel on the same and different axle. Speed, dynamic effect of the wheels on rails. Elasticity of the rails due to better shock and vibration absorbing property. Load taken by the sleepers will be less. Efficiency of the fastening depends on the good connection between the sleepers and rails. Strength of the sleepers, greater the strength, better will be the load bearing property. Track modulus, degree of compaction of the ballast and formation below governs the value of track modulus. Maintenance of track, stiffness of rails, greater the vertical stiffness of the rail, lesser will be the load borne by the sleeper. Stresses in ballast. The transmission of pressure from the sleeper to the ballast depends upon the elastic properties of the sleeper's degree of compaction and the nature of ballast bed. Bigger says and the greater section of the sleeper with longer sleeper length will result in decreased pressure on the ballast and formation. Geometric design of track. Geometric design should be such as to provide maximum efficiency in the tracking of in the operation with maximum safety in the reasonable cost. Gradient, it is a rate of rise or fall of the track expressed in vertical is to horizontal. Purpose of providing gradient, to provide uniform rate of rise or fall, to reduce cost of earthwork, to reach different station at different levels. Types of gradient: ruling gradient, momentum gradient, pusher gradient, gradient at stations. Thank you.